Any of you guys watching the videos? Are you alright? No? Alright. If you watch them, you can turn the closed captioning on. It gets funny. What it thinks I'm saying. I'm like, did I say that? Sometimes it cusses. I love it. I don't ever freaking cuss. Shit. Alright, so let's see. Let's start off with this here. So let me ask you this here. Let's start off a classic probability problem. So dark here. So if I have in a bag, I got 4 red poker chips, 7 green poker chips, and 2 blue poker chips. Okay, so let's do some basic probability. There's some probability you should kind of already sort of know coming in here. You don't have to, but I want to see who knows. If I pick one poker chip, let's start off with something very, very simple. And let's do something new first here. What's all the things that could possibly happen? And don't go crazy. Don't say, well, as I'm picking it out, somebody can bust through the door and knock me over. No. I mean this. If I successfully pick a poker chip out, what could happen? It's crazy, right? Could be red, could be blue, could be green. So that would be what we call the sample space. We normally denote it like in set notation here. It could be a red poker chip, a blue poker chip, or a green poker chip. That's amazing. So sample space is a listing of all the possible outcomes. So these are each outcomes. This process of picking a poker chip would be, believe it or not, an experiment. So an experiment could be something as mundane as picking a poker chip. And that is an experiment because you are trying something out and seeing what happens. So the outcomes of that experiment could be these, and a sample space is a collection of all those outcomes. All right, maybe. So if I picked 2 poker chips, take a second and try to write out the sample space. Question? So this is a little more interesting, right? So what's the sample space now? Red, green, right? Red, blue. So it can be I like it. You got a system going on here, so you don't miss anybody, right? So good idea. Red, green, red, blue, and then green, red, green, green, blue, and then finally blue, red, blue, green, blue. Sweet. Yes, ma'am.
So you know how you have like red, green, and then you have green, red, and then like, why don't you just put that once instead of
Because they're each separate things that could happen. Because I could take red first, and then green second. Mm-hmm. Yes. Cool. I like it. And just to give you an idea, if I had 2 dice, right, and I rolled it and I wanted to get a sum of 13. I wouldn't call 7 and 6 different from 6 and 7 because that is 2 separate ways to get 13. Does that make sense? I mean, the first one doesn't have to be 7 and the second one has to be 6. I mean, there's 2 different ways. I wouldn't just list it once because then it would look like Well, the only way to be officially 13 is if the first one's 7. No, it could be 7, 6 or 6, 7. And of course, other ways too, right? Of course, I don't know. I got a 7-sided die. Let's just go there. You with me? In my brain, I had a 7-sided. I don't know why. So somehow I'm playing Dungeons and Dragons or whatever, and they got a 20-sided die, and or maybe I got an infinite-sided die if you watch Gravity Falls. Anyway, does that make sense? I have to count it because the whole idea of probability is it's based on how many things could happen and how many things match what you want to have happen. Okay, maybe that's enough right now. We don't know enough yet to really explore this mathematically, but hopefully that makes sense. All right, so how many outcomes did this end up having? 9. And why does that make sense? There's 3 things, yeah. So if I'm picking 2, and I'll always make a little hangman game here to figure out the total number. How many options are there for the first poker chips color? 3. And how many for the second poker chip? 3. So there's 9 total. Makes sense. There's 9 total in my outcomes. I can kind of know ahead of time how big my sample space should be, so I know if I left anybody out. All right, how we doing? Now let me ask you this question: do you think that these would be equally likely? Yeah. No. Why not? Because there's different age. So in fact, we should know. This is the part you should come in knowing. What would the probability of getting a red? And this is how I write. This you say this. Say, Jeff. This is the probability of a red chip. All right? And this is much like algebra. Oh shit! I said there wasn't much algebra, and there isn't. But how would you say this? F of X. Good. So this is the probability of R, and R is a red poker chip. What would that be? What is the probability of a red poker chip?
4 out of 13.
4 out of 13. I like it. Because there's 13 total things that could happen, and how many match what I want to have happen here? 4 of them. So how many chances do I have to get a red poker chip? 4 out of 13 total. Now, can you understand why somebody would tell me the answer was 1 out of 4? What is that person thinking? I get people that tell me the answer to that question is 1 out of 4. Because they're saying there's 4 red and I want to pick one of them. But that doesn't really capture the idea of probability. Probability is all about the chances you have. There are 13 things that could happen. Out of those 13 situations, there are 4 that are favorable to you if you have money on red. Right? For example, somehow in Vegas now, they had their decided to die, and people are like, wait. All right, cool. We don't know yet how to calculate these probabilities. We don't. But which one of these do you think would be the least likely? Yeah, blue, because there's only 2 of them. Shit. So you have to be like perfect. It's blue on the first one. There's only one that you have to get blue on to be perfect, right? All right, cool. That should make sense. So later we'll actually show that. We'll be able to show that that's true. All right. How are we doing so far? And this is not a very exciting example, but it's a nice one because almost all the freaking terms came out. Let me see if I missed anybody. Blah, blah. Blah, blah. So let's do this. All right, good. I'm not getting there yet. Okay. So let's really investigate, and I love I always got to bring my little brother up because I tell him I still talk about him. He says, yeah, this is several years ago. He said, Jeff, you teach that probability stuff, right? I went, yeah, Jim, I do. And he said, well, what is that crap? That's a bunch of crap. Because he says, either it's going to happen or it ain't. So everything's 50-50. All right? I'm like, Jim, man, I'm so happy you didn't become a doctor. Those poor patients, routine surgery, you're about to go under. What's my chances, doc? 50-50. Like, damn. And the chance it's going to snow today, 50% chance. Because it's going to happen or it ain't. And I think the chance is freaking 0. It's probably negative shit. Alright. Obviously, Cam, negative probability. Let me make sure you understand that. You're all going to go somewhere and go, my teacher said negative. What's the lowest probability to be? And what's the highest? 100% or 1 is a decimal. Kick ass. Obviously, right? I know you can psychologically give 110%. but you can now have a 100% chance of winning a game. That means like you won that game and 10% of some game that's happening across town. I don't know what that means. I don't know. That's weird. All right, so let's do this. Let's go to the other classic place for probability. Flipping a coin. That's exciting. All right, so let's do something remarkably simple. If I flip a coin, what's probably going to tails? 50%. So one tail out of two sides. One side has a tail, which is the same thing as saying 50% chance. And I see now, you can see where people have misunderstandings very easily. If I flip a coin once, it is going to be a head or a tail, and this makes people think like it's going to be half of something. This probability doesn't really apply to very small samples, especially one thing happening. And that's when James is like, it's going to happen or it ain't. It's 100% or 0 in that perspective. Do you guys see what I'm saying? It's going to happen or it ain't. And that's not what probability is all about. That's like, well, yes. What probability tries to do is to tell us what's the best course of action in any given situation, right? It's saying, I don't know what's going to happen. Let's do the best thing I can. How are we doing so far? I like it, baby. And we do that all the time. When I'm going to go home, and it kind of sucks when I go home because I go down to 125 and about 4 o'clock it's like really congested right there. I'm like, I shouldn't have any traffic because I live in the right place, damn it. I'm trying to set it up so I'm going, everybody's going this way in the morning. I'm like, ah. And the stupid little 125 is always congested. So I do what I can. I go the route that I think is the most likely to be least congested. You understand what I'm saying? So we do things like this all the time. But we don't really understand what this means. So what is that number? What does 50% mean? I don't know. So here's what it is. You ready? This is really nifty. This is not something I made up. There is something called the law of large numbers. That's just an awesome name. And another thing this is known as, basically, is related to the law of averages. Everything's going to average out. If I hit 4 red lights, I'm probably going to get some green lights so that it averages out. Psychologically, it doesn't feel that way, especially if you're late. Every damn red light. Damn red light. Yeah, so I can understand. So what this means is if I flipped a coin 4 times, would I be freaked out to get 4 heads? Would that freak me out? No, you wouldn't go, holy shit! No, you go, all right. You go, what am I doing with my day? I'm flipping a coin. Now, it's about to get worse for your day. So if you flipped a coin 100 times, though, and got 100 heads, 2 things, right? One, again, what the hell are you doing with your life? Secondly, you're freaking out. What is that good evidence for? If you flip a coin 100 times, and it comes out 100 heads, more than likely something's wrong with that coin. Is it impossible for that to happen? Yeah. It is not impossible. It is not. And this is the thing that our brains can't process. Our brains are like, I've never seen that happen. I don't see that ever happen. And in fact, if I ask you guys to write what you think is a random selection of tails and heads, you guys would probably do something sort of like this, where it's sort of changing a lot. But in reality, what happens is you'll get a nice long string, more than you think is going to happen. In fact, does anybody have a coin? All right. Let's do several of you guys. Cool. Everybody's got a coin available. You don't have to give it to me. I'm going to ask you. I'm going to trust you. Oh, it's a big. Yeah, that's right. Throw me. Make it hail. That's great.
I got tails.
So you guys got that? All right, go ahead. If you got a coin, flip it 10 times. You can just flip it and then record what you get. Flip it 10 times. The rest of us will just sit there and wait. And we'll be lunging for the coins as they fall. Holy crap. I should have had a flipping a coin class before this. I'm sorry, people that are around them. You guys are really bad at this.
How many times is that?
Today was the day to wear a helmet. Are you guys done yet? Anybody done yet? Alright. Tell me what.
Tails, heads, tails, 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 heads, tails, heads, tails, tails.
Alright, so you got a string of 3 there, and a string of 2 there, right? Who else? Oh, crap. Yes, sir. Alright, cool. You had a string of 3 there, a string of 3 there. I like it. Yeah.
Tails, head, head, tails, 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 head, tails, head, tails.
Alright, so you had a string of 3 in there, a couple, yeah. Anybody else have like a...
I had like a really bunched up one. I had
Really?
heads, tails, 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 heads, tails.
I like it. I like it. And that, I'm sorry, the rest of you guys that participated. Anybody else have something freaky like that happen?
I have heads, tail, tail, tail. Heads, 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 heads. And then tail, tail.
Alright, cool. I like it. Look at that. 4 in a row and 3 in a row. Sweet. And you had something like that too?
Sort of. I had head, tail, head, tail, head, tail, tail, tail.
Oh, that's cool. I like that one. Sweet. And see, nobody, if I asked you to just write a random string of H's and T's, nobody would ever write that because you'd say that's not random, when actually that is completely random. In fact, if you flip a coin, 10 kind of leaves it open to maybe this is not going to happen, but if you flip one 50 times, I'll bet you a large amount of money that you'll have 6 of something in a row. It's more likely that that will happen than it won't happen. Right? And it's just so counterintuitive. So I said this on the first day when we did, I think we did the whole birthday thing on the first day, right? Didn't we do that?
Yeah.
That most probability is counterintuitive. The human brain is just not wired. Evolution, we didn't have to know probability to survive, so the brain said, well, screw that shit, let's just survive. All right, now we're like, probability helps us, and we don't understand it, we're shit. We're not hardwired to understand it. So here's my point of this. There was another point to this, besides just random strings look less random than what we believe. Random doesn't mean what we think. In fact, I love the comedian that talks about nowadays random means, people don't know what random means at all. Well, that's so random. They're wearing like white shoes, right? Whatever. That's not random. So the law of large numbers says if you do something for a long time, in fact, here, this probability is something called theoretical probability. And just to show you the counterpoint to that, for this person here, this person right there, is it 1, 2, 4, 5, 6, 7, 8, 9, 10, 11? Neat. It's probably me did something wrong. Let me just erase you. For this person here, what was the probability that they would get tail 1, 2, 3, 4, 5, 6 out of 10? So 60%. So you just said 10. There. Now, are we worried that that's not 50%? All right, so this is what's called empirical probability. So if you ever take a class that has the word empirical somewhere, it's normally like a science class, or this is kind of like math science, statistics. Theoretical probability is when I actually don't do shit. Did we do anything here physically? No. Right? We just remember there's 2 sides to a coin, and one of them is a tail. 1 out of 2. Theoretical probability. We didn't do anything. Versus empirical probability, which is where you actually base it on observations. And if you have a small sample, almost anything can happen. If somebody got a string, now here, if somebody got a string of 10 tails or something, we would be a little freaked out about that, right? I would be a little freaked out about that. Not to the point where I'm running out the door and saying, holy shit, get CNN. No. Right? But still, it would have been like, whoa, that's weird. Because it's not very likely to happen. So here's what happens. The law of large numbers says the more you do something. So we did n equals 10. We did 10 flips of a coin. So if I did it n equals 100, if I did n equals 1,000, I would expect the number of tails. So here the number of tails could be 6. Here the number of tails could be 54. Here it's got to start getting really close to 50%. So the larger your number of trials, the more you run an experiment. So every flip is an experiment. Let's do it. We get a tail. Tail is the result of that experiment. Let's do it again. We get a tail. So every time we do it, it's an experiment. And if we do an experiment, if we do it a lot of times, it must approach the theoretical. So if we do something, the more you do something, the more the theoretical probability, I'm going to call that PT, is that right? There's a lot of letters in theoretical probability. That has got to become equal to the empirical probability, or get close. They must approach each other. The empirical must get close to the theoretical. I'm going to let you absorb that for a second. And this is exactly why, if you flipped a coin 4 times and you got 4 heads, you're not going to freak out. But if you flipped a coin 100 times and got 100 heads, you are going to freak out. For a few different reasons, but yeah. You guys kind of see what I'm saying? So at 100 heads, wouldn't you freak out still if you got 100 coin flips? If you got 90 heads, that's still way more than you expected. How many do you expect if you flip a coin 100 times? Somewhere around 50. So if you get 47, you're like, all right. If you get 53, all right. You know, starts getting 60, 70, you start going, wait a minute. And later in this course, we're going to start to figure out, well, what kind of bounds? When does it start to get freaky? We're going to try to actually officially define where freaky happens. Right? Well, this wouldn't be freaky, but once you get past this, that's freaky. And to make it a little more formal than freaky level, that would be evidence of something happening. So if I thought somebody's coin was weighted, they're cheating at games, wherever you use a coin. And I think it's weighted towards heads. And I flip it 100 times and I get 85 heads. I'd say that's evidence that my theory is correct. It looks to be weighted towards heads. Are you guys with me? Or you got dice and you roll dice 80 times and you get ones on each 90% of the time. That is evidence that it's weighted to come up on ones. Right? I don't know why you want to do that. Something maybe do something. You guys kind of with me here? Not a lot of craps shooters, that's all right. Don't play craps, kids. It's weird. All right. I love math, and I don't like craps math. I'll tell you that. Okay. Maybe you guys are with me. So I love that law of large numbers. It just captures the idea. And you guys play poker at all? Any poker players? You know, do you incorporate pot odds or number of outs or anything like that? Or you just go, I'm just going to play. I play for Oreo cookies. I don't know. Or does anybody like play for money? Yeah, you play for money?
Sometimes, yeah.
Sometimes. So do you know what I mean when I say pot odds?
Well, yeah, you're trying to think of, like, what's the chance of, like, the dealer putting, like, another card in your favor.
Exactly. So you think about, what is it that I'm working towards? So if you've got a 2, 3, 4, 5, you want that 6. Or is that enough? 2, 3, 4, 5, 6. So that you get a straight, and what's the odds that you're going to get that? You're going to have that happen, right? So pot odds is even more common. I don't want to get into all of it. But when you're playing poker, you think about what's the probability of this happening and me winning. So this is the way it works. If there's a 60% chance that you'll win on something, that's pretty good. It doesn't mean you're going to win. So with poker, for example, poker is a really good example of this. If you're a really good poker player, you're okay. You understand going in that you're going to not get to the final table a lot. Have you guys watched poker ever? Anybody? I know it doesn't sound like a very exciting thing to do, but actually it's kind of nifty. Well, you probably do. Yeah. All right. If there's let me transition to something else. If there's a 60% chance that some deal was going to make a lot of money, right? So 60%, somebody comes to you and says, "There, invest in this." There's a 60% chance it's going to make a lot of money. Well, there's a 40% chance it ain't, right? But what this means is, if you had a chance to do this kind of deal many times, then 60% of the time it would actually make a good amount of money. So it's a long run strategy, right? So you can't use any individual probability right then to mean something real. That's just the way you play, because eventually it's going to go your way. This is better than better than 50-50, right? So it's got to lean your way. So if you do it enough, you're going to win. So that's one way to kind of play poker, is go down the avenues where the probabilities are highest. And then if you play enough games, you'll get a win. What do you think? Okay, good. So that's sort of like, that goes along with this law of large numbers. So if you do something enough, so for example, even if there's, I don't want to make anybody feel bad, but there's a 90% chance that a surgery will be fine, that you'll be fine. If they do it enough, there will be people that don't come out of the surgery well, right? Because there's a 2% chance they won't. 3 Mile Island. If I say 3 Mile Island, do you guys know what that is? You're like, is that a video game, Jeff? What's 3 Mile Island reference?
The 3 Mile Island is in reference to a now deactivated nuclear power plant in Harrisburg that almost had a meltdown.
Exactly. And there was an interesting required set of things that had to happen for that to almost occur. So there was, for example, there was a little emergency button that if it flashed red, that would mean something bad. And the little light had burned out, for example. So that's one thing. There's a chance that could happen. It's a very low chance, but that doesn't mean it's never going to happen. It just means that it's not going to happen very much. You guys kind of with me? And then there's a person whose job, they get a little clipboard, and they walk around, and they check the machine itself. They see, oh, look at the machine, it's not doing well, or something, right? And that day, as they're walking past the machine, they happen to get distracted, and they missed something there, and they didn't see it. There's a chance that's going to happen. It's not a very big chance, hopefully. You don't want the guy checking the machine to actually do that all the time. But we're human. There's a chance that's going to happen. Are you with me? So maybe there's like a 1% chance that light's going to burn out, and there's a 1% chance that person's going to, and we're like, holy shit. So those two things happening at the same time will not happen very much. But if it's in operation for a while, the chance that it will happen will get bigger. Because as you go over time, there's a more and more chance that something like this is going to happen. 1% doesn't mean it ain't going to happen. 1% just means it's not going to happen very much. It can happen at any instant, right? Maybe. So there's a really interesting thing called, I might bring this in next time, normal accident theory. Actually, I'll bring this up later in the class. This is kind of nifty. So when we get more into the normal curve, I've used that word before. What is a normal curve reference? Bell-shaped. So in this instance, this area would be all the things that could go wrong do go wrong. They all go wrong. And this would be nothing goes wrong. Everything's perfect. So most days, what happens most days, some things go wrong and some things go right. You still with me? But I don't care how, now I want nuclear power. I do. But this sounds like it's an argument against it. No matter what you do, you can never get to 100% safety. You just cannot. It's impossible. So the whole idea of normal accident theory is just to keep us aware. Don't become complacent because we got all these safeguards. Just because you make something really unlikely to happen doesn't mean it's never going to happen. That's not what it means. And as humans, we sometimes think that. Oh, 1% chance? That ain't going to happen. Right? Now, San Diego, of course, predictions of rain, we live in a weird probability. Probability doesn't mean what it's supposed to when it comes to rain in San Diego, right? 40% chance of rain means it ain't going to rain. 80% chance of rain means you get cloudy for sure, and we might get some drops, right? Anyway, sorry. I miss rain. All right, let's come back down. That's a very kind of conceptual level here. Let's bring it back down a bit. All right, good. Yeah, let me do this. Let me do something very specific now. So let's say I poll a few people. I survey people. Right? It's not Family Feud also. And I asked men and women a certain question. And here's the people that said yes, people said no, people said maybe. So, I don't know. will you vote for Donald Trump? Or something. All right, let's not get too deep into politics. Or, hair pieces. Comb-overs. So, whatever the question is, I'm going to let you imagine what the question was. Let's see, 11 a minute. Well, I'm not going to say, I'm trying not to say too much about what this all means here. Alright, so that's the results from me asking these people questions. So, let me ask you something real quick to make sure that we can read this correctly. How many women said no?
21.
21, good. Alright, just to make sure we're all looking at this correctly. I'm always a little surprised at how people can look at this incorrectly. Now help me out. How many total yeses were there?
18.
Yes, there's 18 total yeses. How many total no's?
77.
How many total maybes? How many men?
How many men?
20. How many women? 35. So how many people? 55. So that's got to add to be 55, and that's got to add to be 55. That's how you can kind of check yourself. Why would somebody put 110 there? I guess people will put 110 there. That's wrong. Why would somebody do that?
You add up.
Yeah, they add these people and these people, but they're not different. You added people twice. How did you do that? Right? It's like going up for samples in the grocery store. Oh, somebody different. That's right. All right. So let me ask you some basic questions. And this form. This table is a form that I often use with the data that you gave me on that anonymous survey. So like on a quiz or a test, I'll give you the data right back at you that you gave me and ask you probability questions. So just make sure you guys are aware of this. Let me write this down formally. The formal definition of probability. And then I got to glance at the clock. I have no idea how much time we have. Oh, we have plenty. And I was like, shit, why did you notice? Formal definition of probability. So the probability of some event A. And we normally use the letters A, B, C for these events. And an event could be, I pick a red poker chip. An event could be, I pick a blue poker chip while tripping over a dog. So an event could just be defined in any way. So the probability event would be the total number of possible outcomes goes on the bottom. And the top would be the number of outcomes favorable to what I want. Does that make sense? I always have trouble figuring out how to say that. So what I mean by that, let's do an example here. Let's do a concrete example from this. Number of outcomes favorable is what that says. I think that's Swahili that I've written up there. What's the probability that if I pick somebody from this sample, let me give us a lead in here. Pick one person from the sample above. What's the probability that I pick a man?
20 out of 55.
Exactly. So the total number of things, in this case people, that could have happened is 55. If I'm picking a person out of this group, 55 different outcomes could have happened, right? Out of those 55 things, how many match what I'm looking for? 20. All right, cool. That is the basic idea of probability, and that idea actually never changes. We're going to have a bunch of probability formulas, and I'm going to try to make you realize they all come back to this basic definition. Now, what can I do with that? I can reduce it, make it 4 out of 11. I can divide it, make it whatever the hell that is. 37? I don't know. 36.4. All right, have a look at that. Anyway, you guys with me? All right. When you're doing a quiz or a test, this counts as your work. This is writing that in a different form. Are you with me? This is your work because this is where you apply the idea of probability. If you just give me a percentage, I don't know where it came from. If it's wrong, I don't know what happened. So again, you got to show me work, and this constitutes work for basic probability questions. Okay, so let's try a couple more from the same group of data. Let's probably pick somebody who said no. 27 out of 55. And then you can make that into percentage if you want to. Somebody help me out. What would that be?
49.1%.
Who do?
49.1%.
49.1. All right. Cool. So let me make a little. Yes, sir.
Oh, no, I'm good.
You're good? Okay. So let me make a little more interesting question. Let's probably pick a person who is a woman and they said maybe. So how many people match what I'm looking for?
7.
7 people match what I'm looking for. You guys see that? So and will always make the number smaller. So back in the day, children, most of you guys are younger than me, we had this, nowadays to find a scholarship, I don't know if you realize how easy it is compared to what it used to be. So we used to have to go to the financial aid office and they had this giant book of scholarships. And you start to read through and you go, to get this much money, you must be planning on being a math major. Check. You must have this GPA. Barely check. You must have this and this. And then I'm like, check. And, right? So the number of people who would qualify for the scholarship gets smaller. I call that the mean bouncer. Right? To get into a club, they're like, guys, you got to be rich, and you got to be good looking, and you got to have good clothes. Right? I'm like, I'm 2 of those things, maybe. Right? Well, actually, I'm none of those things at all. Too bad. And will always make the number smaller than normal. So women, probably a women would be 35. There's 35 women out of 50. Maybe would be 10 out of 55. But the people that are both of those will be at most one of the smaller one of those numbers. But here it's 7. Because you've got to match both things. So I know the top is going to be 7. Now here's where people freak out a little bit. What's the bottom going to be? 55. I mean, did I tell you anything about the person? Do you know anything about the person? Did I say anything about what the person is? No. So picking one person at random, what's the probability I get a person who's both those things? So which people could it be? Any of the 55. So what's the only time the bottom of a probability will not be the total in the sample? If I tell you something, if I said, oh, by the way, it's not a dude, then I can eliminate all the dudes. Boom, they're gone. And the bottom would have been 35. Because then I'm only looking at the women. You guys...
Like if it said out of all the women, how many said maybe?
So here's how I would say it. Since we're talking about it, here's how I would say it. What's the probability that I get somebody who said no, given that they're a man? So be careful. What is it that I know about the person? No. In English, what do I know about this person? They're a dude. Given that they're a man. So what's the bottom going to be? You can immediately tell me that. Yeah, the bottom's going to be 20 because I'm talking about men. So I can just cover these up. I'm only talking about those people. I'm going to throw all these people out. So out of the men, given that it's a man, so I'm only talking about 20 people. Out of those people, how many match what I'm looking for? 6. So there you go, 6 out of 20. And that's an easy one to make. 30%. Yeah, I like it. All right. Now watch this. Did I do this? Yes. Well, no, shit. That's not what Oh, here we go. Perfect. What's probably that somebody says no? You write that a little better. 49.1. What's the probability that I said no if you know it's a dude? So would you say that being a dude affects the answer to the question? Let me say that again. Would you say that being a dude affects the answer to the question? Of course I would, right? Just make sure you guys know you were right. Just make sure everybody got that. Totally, these two things affect each other. being a dude, changed the probability that the person said no. Does that make sense myself? I'm covering a lot of ground here. We're actually doing several sections today, all at once. All right, later we'll come back and we'll split them all up. But these ideas run into each other. I do this every time I teach you because there's no other way to do this. So watch this. If you saw off in the distance a person walking towards you, and they're so far away and you can't tell if it's a man or a woman. This is probably it's a man. 50%. That's your best guess, right? So 50-50 chance. 50% chance is a man. Then somebody said, oh yeah, that person just got off that Harley Davidson. Is the probability it's a man, does that increase or decrease?
Increase.
Now, did I just say that no women ride Harleys? Did I say that? This is what people don't understand about probabilities. The probability increases because of what they just did. It's more likely it's a man because who rides Harleys? More men are Harley riders than women. I didn't say no. So the probability is not 100%, but it definitely went up. It's probably a dude. I put money on it being a dude, right? And when the girl gets there, she'll say, no, man. I'm sorry. It's just the way the probabilities. It's the odds. All right. Maybe. All right. How we doing? So this is the idea of conditional probability. And why does that word make sense? Because the probability that the person said no changes based on the condition of, are you talking about a man or a woman or just anybody? So let me see. Probably somebody said no is almost 50%, right? It's 49.1%. Probably that said no if they were a man is 30%. So what do you think about probably no given it's a woman? They're going to have to be bigger than, it's going to have to actually be bigger than, because it sort of averages out there. So let's try it. What is the probability that somebody said no given it's a woman? So what goes on the bottom now? Yeah, there's, where are you at? There are 35 women. Out of those women, how many said no? 21. What's that, 60%? Is that true? Let's make that up. Yes, it is 60%. So does that kind of, do you see what I mean? Those 60 and 30, they don't average to be this, because of course there's more women than men, but it definitely had to be on the other side of 49.1%, so it would make sense. If you're a man, you said no less frequently than if the women said no. Right? So whatever issue this is, it has some kind of gender dependence. How are we doing so far? So do you notice the word I just said and nobody looked at me weird? Dependence. Why does it make sense to use that word? Here, I would say that the answer you give to the question and your sex are dependent on each other, right? If you're a man, your answer to the question is going to be different. There's going to be a different probability for the answers to the question. Does that make sense to use that word, dependent? Yes, ma'am.
Does that apply to the one before, the probability of women and maybe? Is that also?
No, because in this one, I didn't know anything about the person. It's not splitting them up into groups. So this is actually the most fundamental thing we do with probability is we say, for example, I did this with my other class. I said, I might have done it with you. No, not yet, because I haven't looked at enough homework. But I said, everybody who did 2 or less homework assignments, the probability of you making a good grade was this. And everybody did more than 2, it was this. So you split them up into groups and you see if there's differences. That's the basic idea of exploratory statistics. And then you go say, why is there a difference? So whatever this question was, if you didn't expect this, if you're like, whoa, why were there 30%, if you're a man, you got a 30% chance of saying, no, why is that? And then you go out and do some deeper study. Why is that? What is it about this that makes it happen? Maybe. I don't know if you guys are with me. All right. So let me ask you this question. We haven't done this yet. So given this again, still, what's the Roman numeral in this? There you go. What's the probability that I get somebody, still I'm picking one person, somebody who said yes or they're a woman. And this gets interesting. So and is very restrictive. The numbers go down because you have to do all the things. Or is the nice bouncer. The nice bouncer at the club says you gotta have a lot of money. Shit. You gotta look good. Shit. You gotta have nice clothes. Shit. Or you gotta know Fred, the bar. Oh yeah, Fred's my friend. Right? I don't have to have all 4 requirements. I just need any of them or any combination of them. You guys. So or is nice. It makes it big. More and more and more people could come in then. The and bouncer's me.
So for this, would you add the yes being 7? Or no, yes being 18.
All right. So I got, let's see, 18.
And then plus 35.
Plus 35.
Out of the 55.
All right, that's a good guess. Good guess. Not quite right. Why is it not quite right?
Because then you're adding in the 7 women who said yes along
Yeah,
with
these
the
guys get added in twice if you just do that. All right, let me let that sink in for a second. That can't be right because I've counted some people twice.
So 7 plus 28 would be?
So what I can do, one thing I could do is just subtract the people I've counted twice. So let me formalize this a little bit. Let's see what this really looks like. You ready? So the probability of A or B equals the probability of A. Let me stop there for a second. Is that cool? So it's probability of yes. 18 out of 55, right? What's probability of women? 35 over 55. Now, how would you characterize this piece of it? 7 out of 55. What is that? Who are those 7 people?
The ones that are women and said yes.
And, good. So that would be minus the probability of everything that is both, because you've counted them twice, so you've got to subtract one of them off. That is the official formula for OR in probabilities. Does anybody, I think you guys started to say this a second ago, and I cut you off. Isn't there a better way to set this up in the beginning? If I do 18 yeses, or even better, if I do 35 women, how many people have I not counted yet? 11. So I could do 35 plus 11, right? Does that make sense? So when you have a situation where you can count everything, the formula sometimes is too much. I don't need all that. I don't need this whole thing. I'm going to get the same answer. Because what's 18 minus 7? Holy shit. So I'm going to add 11 and 35. So I could just say all the women have to be included, right? All the women. And everybody said yes. Oh, I already got you guys. I just need you guys. So you can be smart about how you put it together. What troubles me is when people do this. No. Don't do one or the other. Either do the equation itself or just get everybody you need by counting. You don't have to use a formula, just get what makes sense. Maybe some of you guys are with me. You can always fall back on the formulas, which will be on your formula sheet. But sometimes the formula makes it harder than it really should be. Why do formulas do that? Not because they're evil, but because they have to be the most general they can be. And that's a hard thing to do. So then this will be where L 46 out of 55 is. Maybe. So a real quick example. Watch. Here's something that I get on a quiz or a test. What we got? Women or no? I'll get somebody to do this. Ready? Don't even write this. This is wrong. They'll say, like we did earlier, they'll say, all right, 35 women plus 27 said no out of 55. 35 and 27 is 62 out of 55. Why is that math yelling at you, hey, person, human, you have done something wrong? It's bigger than freaking 1, right? So what is 62 out of 55?
1.127.
So it's about 112.7%. That is desperately saying to you, wait, you've done something wrong. And this is, you go, oh, we forgot to subtract people off, right? So please, if you ever get something that is more than 100%, or 1 if you write it as a decimal, right? Don't just leave it. If you can't figure out what you did wrong, at least say, I know it shouldn't be this, but I can't see what I did wrong. At least say that so that I know you don't believe that could be the answer. You will lose more points if you don't say anything. Does that make sense? I mean, that's basic. That's like that. That's just telling you, hey, you made a mistake. Go back. Hey, wait, no, don't go to the next problem. Shit. All right, so what should this be, of course? Yeah, I can do 35 plus the 6 no's that I haven't counted yet. Or I could do 35 plus 27 minus 21. 27 minus 21 is 6. That's crazy. So you're going to get 41 out of 55. Yay. It's at least less than 1. So I'm on the right track in that respect at least. All right, cool. This makes me cry a little bit when I have somebody give me a bunch of things that are more than 100% chance. I mean, what does that mean? 120% chance of rain. It's so going to rain. It's going to be like, oh, monster. No. Okay. How do we feel about that? I think you might pick up on the fact that I like this. This was remarkably simple. And look at all the freaking questions I can ask. Yeah. It's awesome. Okay. So here's a different thing. Let me see. Yeah. So let me come back to some definitions. Let me ask you something silly. Okay. All right. The probably is going to rain today. And actually, there's supposed to be probably. So let's say it's 10% chance. What's the probability it's not going to rain? 90%. Actually, I didn't check on this. Normally, you have a little, not on top. I wonder how they do this. I'll show you how. Oh, I see. Oh, crap. They do that. Shoot. All right. I mean, not crap. Where's the crap? So they use that to mean not rain. If I write this, that's what I'm used to. That means not rain to me. Or you can actually, use the word not if you're weird like that. So that, of course, is going to be what again? Sorry? 90%. So the probability of not A is how related to the probability of A?
100 minus probability of A.
Yeah, and normally when we write it like this, we'll use decimals just to cover our ass, because math doesn't really like percentages. 1 decimal, right? Not 1%, but 1.0. So we'd say like this is 0.10, that's the true number. This is 1 minus that, so 0.90. Kick ass. All right, that's pretty basic. We call this the complement of the event. That's the E instead of the I, so it's not saying, hey, you got a nice looking,